The question says a stationary coil of 35 turns. I will keep writing whatever is given in the question. It becomes easy to recollect which formula to apply. So 35 turns and cross-sectional area of, I'll write the area as 0.02 meters square. Is placed between two electromagnets and connected to a voltmeter as shown. The electromagnets produce a uniform magnetic field. Okay, so magnetic field is given as 0.15 Tesla. The magnitude of the magnetic field is then reduced to 0. So we have a variation in the magnetic field. So I can write that this is B1 is the initial magnitude of the magnetic field, and the final magnitude is given as 0 Tesla over a period of, so delta T, that is the period during which this change of B happens, that is given as 0.4 seconds. All right, calculate the magnitude of the EMF induced in the coil. So do you recollect the formula to be used? EMF induced is equal to minus N d phi over dt. Yeah. And what is the relation between phi and B? So that is given by phi is equal to B dot A. Yeah, that will be equal to B A cos theta. My stylus is not writing very properly, but I will try to make it as understandable as possible. So what is theta over here? Theta is theta over here. So in the picture, if we see, this is the area. If we see, this is the area of the coil. So theta is the angle between the normal to the area. So the normal to the area and B, and B is already shown as pointing downwards. Yeah, so it depends in which side you draw the area. So if I would have drawn the area as over here, then I would have seen that the normal to the area makes an angle of 0 degree with the B, yeah, magnetic field, and in this case it makes an angle of 180 degree. So whichever be the case, yeah, so cos 0 or cos 180, so cos theta is equal to 1 in our case, and therefore phi will be equal to BA. Yeah, put both the things in the given equation. So it says only magnitude. We have to calculate only the magnitude, but we will go ahead with the direction as well. So E will be equal to minus N d by dt of B into A. So in the given question, what is changing? Is it the B? Yeah, so B is definitely changing. Is the A changing? No, A is a constant. Therefore, bring the constant outside of this expression. So it will be equal to minus N into A into dB upon dt. Yeah, and this can further be simply written as minus N A into delta B upon delta T. Yeah. So therefore, this value will be equal to minus N into A into B2, final value of B minus B1, yeah, divided by the time difference given delta T. So we just put the values given. So this will be minus N 35 into A, which is 0.02, into B2 is, this will be, B2 minus B1 will be negative, so this will be 0.15. The stylus is not writing very properly, so excuse me for that. So this will be, but it will be negative, so that negative and this negative will become positive, and divided by the delta T value, which is given as 0.4. So if you do these calculations, what do you get? How much is the value? It will be, I will do the offline calculations, and I will just write the answer over here so that the question becomes complete. So let's take an add-on question to this. If I say that, if I ask the question, what is the direction of the induced EMF, yeah, or the direction of the induced current? The direction of B is given in the downward direction, and we know from the Lenz's law that the induced EMF or the current in this coil will be in such a way that it will try to oppose the change. So in this case, the change is that there is a magnetic field which is decreasing from a constant value to 0. So opposing means it will try to increase the magnetic field, and therefore the induced magnetic field will be in such a way that it will try to be in the direction of the external magnetic field, and therefore this will be, maybe I can put it as BI. Yeah, induced magnetic field will also be in the same direction as the one external one which is reducing. That's because it will try to strengthen, it will try to oppose. Since the external magnetic field is reducing, so it will, the induced magnetic field will be in the downward direction, so that it will try to strengthen, it will try to increase the external magnetic field, or you can say the overall magnetic field. So if the direction of the induced magnetic field has to be pointing downwards, so that means I can further show it like this. So which means we know that in a magnet or in an electromagnet, the magnetic field of lines, they flow from the north to the south outside the magnet, and whereas within the magnet they will flow, maybe I can put it over here, it will be S and it will be N. So externally, the magnetic field of lines in the coil will move something like this. Not a good drawing, but at least for understanding it should be good enough. Yeah. But internally, they will flow from south to north. So the moment we conclude that this is the south pole of the induced magnetic field, so therefore south means it is going to be, current is going to flow clockwise. Yeah. So with south pole, it means if you look from the top to the bottom, so looking into the coil from the top, so current will flow clockwise. So if it is clockwise, it will be arrow of the direction of the current will be like this. Yeah. and over here it will be, since it is a north pole, so it will be anti-clockwise. Now if I can put one more question, so instead of a V, if we put a galvanometer, so that is used to indicate the direction of the current. So in which direction the deflection will be there? So since it can deflect either towards left or towards right, in this case the current will flow towards the right, so the deflection of the galvanometer will be something like this. Yeah. If I can add one more question, I put a resistor in the circuit, and that external resistance value is given as, let's say, 1 ohm. So can you tell me what will be the value of the current in this circuit when we have this induced EMF? So that will be, current will be equal to E upon R, and that will be, again, the value will be 0.262 ampere.